Alright, welcome to our intro on kinematics, and this is an extension of our first experiment, which calculated speed. And there you can see my daughter Maeve and my dog Doc, the two test subjects in my experiment. Let's get started. Just wanted to show you the data table one more time. Again, I took averages for both my daughter and my dog, and I used the formula of speed is equal to distance over time. And I came up with Maeve's speed over 10 meters at 2.55 meters per second, and Doc, my dog's speed, at 5.24 meters per second. So we're going to be making motion line graphs to help visualize our data. And the first one is called a position over time graph, and you can probably see why. On the y-axis, I've got position in meters, which is marked by x. And on the x-axis, I've got time in seconds, which is indicated with a t. Please also note that the positive y direction is up, and the positive x direction is to the right. And so now that we've established directions, we can actually look at the speed that we've calculated as a velocity. Because again, velocity is a vector, which means that it has a magnitude as well as a direction. And so now we've established a positive direction both in time and in position. Please also note that the change in position as represented by the line, both lines are parabolas. They're curved lines that slant upwards. You can see x sub d for my dog Doc and x sub m for my daughter Maeve. Now think about that. Why does the position change as it does? Why is the position not represented by a straight line? Think about how both test subjects got from the beginning to the end. Did they travel at the same speed the entire time, or did they speed up? And you know, because they both started from a standstill at 0 meters per second, they're actually speeding up. Now, by using the formula of speed equals distance divided by time, what we actually calculated was the average speed. Or now that we've established a positive direction in both time and distance, we can say we calculated the average velocity. Now we also know the initial velocity, as in the starting velocity of both test subjects. Both started at a standstill at 0 meters per second. And because of that, we can actually figure out the final velocity. Or in other words, how fast was each test subject moving when they crossed the finish line. Please note the symbols in the top of the page, v sub 0 or v naught, v sub f or velocity final, or VF, and then V sub average. So we've got the initial velocity in V sub O, we've got the final velocity in V sub F, and we have the average velocity in V sub average. Now think about this. If you're going to calculate the average of anything, let's say the average age of you and two other classmates, how would you do that? Well, you would take all three ages, you would add them up, and then divide them by 3. And so we're going to do the same thing. We're going to look at the average velocity as being a combination of the initial velocity and the final velocity divided by 2. Now I realize there's a lot going on this particular slide, so please just stay with me as I go through this. What we're going to do, we're going to solve for final velocity. So we're going to take that initial equation of that the average velocity equals v sub o plus v sub f and divide it by 2. That's where we start. Well, what we want to do is we want to isolate final velocity. We want to isolate v sub f. So the first thing we can do is multiply both sides by 2. When we do that, we're going to get 2 velocity average equals velocity initial plus velocity final. Now we can just subtract velocity initial from both sides. And in the box there, you're going to see the equation that we can use for both of these test subjects to find the final velocity. Final velocity, v sub f, is equal to 2 times the average velocity minus the initial velocity. And for us, that's convenient because the initial velocity is actually 0 meters per second. Now below that, I've solved for the final velocity for both my daughter Maeve and my dog Doc. The final velocity of my daughter, the speed at which she is traveling when she crosses the finish line, is 5.1 meters per second. And the final velocity of my dog, once again, the speed at which he's traveling when he crosses the finish line is 10.5 meters per second. And just for comparison's sake, here is a little table to show you the initial velocity, the final velocity, and the average velocity of my daughter and my dog. So here's the second of our motion line graphs. It's a velocity over time graph. And again, you can probably see why we call it that. Velocity on the y-axis is represented with v, and the units are meters per second. And time, once again, is on the x-axis in seconds. So look at the two lines here, v sub d representing the velocity of my dog, and v sub m representing the velocity of my daughter Maeve. How do they compare? Visually, we can see that the dog's velocity is increasing more rapidly over a shorter period of time. So what do those slopes actually represent? They represent the change in velocity over the change in time, which is what we call acceleration. Towards the bottom, you'll see that triangle symbol in front of the V, that is delta, delta V over delta T, and delta stands for the change in. So once again, that's the change in velocity over the change in time, or acceleration. All right, just a few things to consider here. First of all, the lines on the velocity time graph are straight, and therefore they represent constant acceleration, and all the problems that we're going to be working on will in fact be based on constant acceleration. Also, the velocity time graph will show us the velocity at any given point in time. So for example, we can look at the graph and we can find out what Maeve's velocity is at 1.5 seconds, and it turns out that it's 2 meters per second. Similarly, my dog Doc, at a half a second, his velocity is going to be 3 meters per second. And so once again, if you look at my daughter's velocity at 1.5 seconds, it's just about 2 meters per second, as indicated by the vertical red line. And my dog's velocity at 0.5 seconds is 3 meters per second, as indicated by the horizontal red line. Now, obviously, I've drawn this in my notebook, and I've taken care to be as accurate as possible. And I'm also estimating, but it's very close. So we're going to use the formula of change in velocity over change in time to calculate acceleration. And if you look down at Maeve's, you'll see that her change in velocity was 5.1 meters per second. So again, that's her final velocity minus her initial velocity of 0.0 meters per second, excuse me. Total time took her to travel 10 meters was 3.92 seconds. And so if you divide that out, you're going to see that her acceleration was 1.3 meters per second squared, which means 1.3 meters per second per second. So every second she's accelerating another 1.3 meters per second. Doc, on the other hand, his change in velocity was 10.5 meters per second, and it took him 1.91 seconds to cover the 10-meter distance. Again, if you divide that out, you'll see that his acceleration was 5.5 meters per second squared. Incidentally, getting back to the previous slide, if you again look at Maeve's velocity at 1.5 seconds, it was 2 meters per second. And so if you look at that change in velocity of 2 meters per second divided by the time, guess what you get for her acceleration? You also get 1.3 meters per second. And the same is true for Doc. It actually comes out to be 6 meters per second for Doc instead of 5.5, so I'm guessing that my graph is off by just a little bit. If you're asking yourself, what the heck does meters per second mean, or meters per second squared, or how do we come up with that? Well, here's a little explanation on that. So again, we're dividing the change in velocity by the change in time. So 5.1 meters per second over 3.92 seconds. And this is Maeve's acceleration we're looking at one more time. You can also write that a different way. And on the right, you see I've written it as 5.1 meters per second times 1 over 3.92 seconds. And if you do that, you can very easily see how the seconds are combined. Seconds times seconds equals seconds squared, which gives us our derived unit of acceleration for meters per second squared. The final of our motion line graphs is going to be acceleration over time. And so acceleration is on the y-axis. And again, it's represented by a, and the units are meters per second squared. And time is again on the x-axis with units of seconds. And you can see that both accelerations are flat lines, or horizontal lines. And so a sub d, or Doc's acceleration, you can see is indicated there at 5.5 meters per second squared. And Maeve's is below a sub m at 1.3 meters per second squared. All right, so now for both my dog and my daughter, we know quite a bit of information. We know the starting position, x sub naught, or x naught. We know the final position, x sub f. We know the initial velocity, v sub naught. We know the final velocity, v sub f. We know the acceleration, a, and we know the time. And we have a pretty good idea of how those are all related to one another. The next step will be to learn how to solve for unknown values in one-dimensional kinematic problems. Until then, carry on.